Okay, all right. So it has started recording. Let's continue our discussion on Laplace transforms. And today is Thursday, last lecture of this week. And next week we have three lectures. So what I am thinking is Monday and Tuesday. Tuesday we may finish the course, and Thursday I will make myself available during the lecture hour, but it will not be a formal class. You can, if you have questions, you can ask me. That is the plan. I will confirm on Monday. Okay, let me confirm on Monday. Anyway, let's continue discussing. NSEM will be for the not 42. No, we will exam related things. Let me message so that it is uniformly told to all the divisions together. But whatever we said in the instruction booklet, right? So it cannot be 42. No, we said in terms of weightage, right? No, no. What did we say in terms of weightage? Yeah, it'll be scaled up. Correct. Anyway, let's not discuss exam related stuff in the class. It'll be via Moodle. We will send a message. Okay. It's what is written in the instruction booklet. You have to scale it up correctly. So let's start the lecture. Let me start sharing the screen. And as usual, one of you please confirm.
Yes, sir.
Okay.
Yes, sir.
Very good. Okay. So I could have added one more keyword today, which is coming towards the end of the course, end of the today's lecture. It is called convolution. Convolution, convolve, convolution. Okay, that's a keyword in today's class, which will come in the context of Laplace transform. We will see. Okay, but since this is a very, very important topic, Laplace transform in its applications in differential equations, and as a standalone topic also, it's very, very important. So I'm going to recall. So my first few slides will be what we have already done, because I would like to stress, I would like to make sure that everybody understands these things properly. So let me recall and then continue. So some of the examples in last one or two lectures, I will again put it as part of my slides. Okay, pay attention. So first we defined piecewise continuity. What did this mean? This meant you can divide your domain interval into finitely many subintervals, and in each of those subintervals your function is continuous. And what are the kind of discontinuities that can come at those other finitely many points? They are the jump discontinuities. So finite jumps, limits exist, left limit and right limit are finite. They may not match, and therefore you may have discontinuity. So the jumps are always finite. When you say jump discontinuity, the limits exist. Finite limits exist. From right side it exists, from left side it exists. They may not equal. Okay, so jump discontinuity. Except for that, at finitely many places, the function is continuous. Then we define exponential order. So a function is of exponential order, let us say alpha, if there exists alpha and there is some constant which we call k, and there is some other constant which we call m. This is the stage. So that beyond m, you have an inequality. Beyond the stage, after some stage, you have an inequality. And the inequality was of the form modulus of f of t is less than or equal to k e power, if order is alpha, then k e alpha t. Okay, this is what is called exponential order. Then we prove that if your function is piecewise continuous of exponential order, if you assume both, then Laplace transform exists. That integral converges in some region, depending on the order. So where did you prove the existence of Laplace transform? For s bigger than alpha. If it is of piecewise continuity was also used in the proof. So if it is piecewise continuous of exponential order, in fact, you assume piecewise continuity for all 0 alpha, for all alpha positive or something like that. And then 0 AA positive. Then whenever S is bigger than the order, we prove the existence of Laplace transform. this was sufficient. This is not necessary. And we saw an example where piecewise continuity was not there, still Laplace transform existed. And we also saw an example where exponential order was not there, but still Laplace transform existed. Okay, so all this we did. And then we stated Lurch's theorem. And some people call this the Lurch cancellation law and Lurch's theorem. And I stated it. Did I prove it? Did I prove Lurch's theorem? No, right? We skipped the proof. What was the statement? If f and g are continuous functions and if L of f equal to L of g, then f equal to
F equals G.
Therefore, this was very, very important for us because uniquely we can get inverse Laplace transform. That's why this was important. Okay. And then we had a formula for L of f prime. You remember this? What was L of f prime? You had to assume some conditions. Under those conditions, what was L of f prime?
Yes, L of f minus
SL
F
of
of 0.
minus
Yes,
L.
L of f minus f of 0. So basically, it is multiplying by s. And as a corollary, you had the nth derivative where you will multiply with s power n, and then you will subtract f of 0 multiplied by s power n minus 1, f double prime 0 multiplied by s power n minus 2, dot, 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 right? So you had a formula for this. This was proved using induction. So you prove L of f prime, and then via induction, you can prove this. And then you had a formula for this. And what was the key word in this proof? You assume the formula for L of f prime, and then you can prove this using
Fundamental theorem
of calculus. And L of f prime involves multiplication by s. Therefore, L of integral f involves
division by s.
Division by
yes. And the formula for L of f prime was s L of f minus f of 0. And the formula for L of integral of f is L of f divided by
S.
And all these are very, very useful. Then we proved limiting behavior of L of f. What does that mean?
That when s tends to infinity, there must be a finite value. Means
Value or 0?
Zero.
zero. Yeah.
Normal
0.
0
Not finite value, it has to be 0.
for normal functions.
We proved this. Did we prove this?
Yes, I mean,
No.
Yes.
exponential order we
Yes
proved.
and no. Yes and no. Yes, we proved this, assuming that f is piecewise continuous of exponential order. Under
Other
the
things
condition
not.
we proved this. We bounded this by a constant by s minus a. The modulus of L of f, we bounded by a constant by s minus a, and therefore it is true that as s goes to infinity, limit is 0. Then I stated that this is true for any function, and I underlined the word function, saying that things like Dirac delta, it is not expected. That is different. That will also come in this course in the next lecture. Okay, so limiting behavior is that for a function, if you take Laplace transform, then the limit s going to infinity LF is 0. So therefore we concluded, many functions can never be Laplace transform of a function. You can conclude by checking the limit. For example, s minus 1 by s plus 1 is never a Laplace transform because limit as s going to infinity is 1, not 0. Okay. And then did we do L of f prime? So here prime was inside the bracket. That means prime is with respect to t. And L of f prime is a function of s. Now I'm doing L of f. So f is a function of t. L of f is a function of s. And what does prime mean? Prime meaning d by ds here. Here prime means d by ds. Here prime meaning d by dt. Did we do this?
Yes, sir.
Yes, sir.
And what was the answer?
Minus
L of t into f of t.
Yeah, L of minus t into f of t is L of f prime. Right?
Minus L of t into f of t.
Yeah. So there's a minus sign. Either you put it on this side or you put it on that side. And what is the key word of the proof? Not key word, but the keywords, key phrase. There's only one idea in the proof, which is
Differentiation under the integral.
differentiation under integral sign. Okay, very good. Did we do integral of LF?
I don't think so.
I don't think so. But
Here it was L of integral f, and it involved division by s. And here we are doing integral of LF. So LF you are integrating with respect to ds, right? And did we do this?
No, sir.
No, sir.
No, sir.
We will do it today, but you tell me what should be the answer. So here,
Division by t.
yeah. So here, f prime was inside the bracket. It involved multiplication by s outside, and integral was inside the bracket that involved division by s outside. Here, the differentiation is outside that involved multiplication by t inside. From these three pictures, what should be the answer for this? It should be
L of
Division by t.
by t.
division by t. Where, inside or outside? Because it is
Inside.
inside. Okay. So you have got
It
it.
is outside.
Yeah, absolutely. Very good.
Minus sign will be no, sir.
There may be a sign. So let us check. Okay. The actual thing we will check. But just to guess multiplication, division, it will be division. I think there is no sign. The way we formulate, there will be no sign. Because what is integral? I'm going to formulate integral as integral s to infinity. So that will take care of the sign. I think we will see in the slides when it comes. Okay. But basic idea is division by t inside. No, division by t inside. Yes. So we will start by recalling a few slides from the last lecture because these are all very, very important examples. So first example, this was there already last time. And most of you said, you can do inverse Laplace transform by partial fractions, which is true. But the point of this example last time was to use one of those formulas. What is the formula that you used? So what strikes you first? What strikes you first is 1 by s square plus a square. And the inverse Laplace transform of 1 by s square plus a square is 1 by a
Sine of
sine 80.
80.
So that is the Laplace transform of a function f of t equal to sine 80 by a. Therefore, in order to get the inverse Laplace transform of LF by S, what do you do?
Integrate.
Integrate.
So sine 80 by A, you integrate once. You would have got 1 by S times S square plus A square. And that answer, if you integrate once more, you will get S square. So this is what we did. L inverse of this is sine 80 by A, and L inverse of this by S is integral of this. So some answer. And in order to get S square, you integrate once more, you got some answer. Okay, you remember this? This we did last time. Okay, therefore you got the answer. And then we stated this result that there is a minus sign and t you multiplied by inside. And this you already said. The proof was very, very easy. It is differentiation under the integral sign. This is where I went to Google. I showed you the wiki page, and there was this anecdote about who?
In
Feynman.
About Feynman. And what is that book called from which the anecdote was quoted in Wikipedia?
Surely you're joking, Mr. Feynman.
Surely you're joking, Mr. Feynman. Yeah, very good. Okay, so this is what was the basic idea of this proof. And now we will do, yeah, so these were also examples. I just copy pasted the slide again. Okay, so what you remember among these three things, the striking thing is there is a square here. So that tells you what? The square in the denominator tells you
Differentiation with
differentiation
respect to
of 1 by s square plus beta square. And 1 by s square plus beta square is something that you understand in terms of sine and cos, right? The Laplace,
yes, sir.
Laplace transform of what is 1 by sine square plus beta square, s square plus beta square? Sine beta s by beta, right? And S by will tell you something about cos. So which one did we do first in these three things? You remember? Which one was
Second.
Second we did, and using second in order to come to first, will you do derivative or integration?
Integrate.
Integrate, because it is second by S is this. So you do second first, and observe that first is second divided by S. That tells you you integrate the answer. And third is second multiplied by S. That tells you differentiate. Okay. So recall quickly. L of cos beta t is S by S square plus beta square. L of sine beta t is beta by S square plus beta square. Therefore, L of t into cos beta t with a minus sign, this will be derivative. And that you got this, and similarly t into sine beta t minus of the derivative with respect to s, you got this, and therefore you already got s by s square plus beta square whole square. You divide this answer by 2 beta. So answer is t sine beta t divided by 2 beta. And in order to get 1 by s square plus beta square whole square, this is Laplace transform of this. You can see my cursor moving, no? So this one is Laplace transform of this. So Laplace transform of this divided by s will be integral of this. So this is integral of this. Whatever you get is the answer. And this is multiplying the Laplace transform by s. So what you know is s times the Laplace transform minus f of 0. That you know. And f of 0 is 0 here. If this function you call f of 0 is 0. So this is s times Laplace transform of f minus f of 0. So L inverse of that will be L of f prime. So L of the derivative of this. So the derivative of this is the answer. D by dt of this, whatever it is, you can do. Okay. So now let's come to L of. So what should I do now? There are 4 things. L of f prime that we have done. L of integral of f that we have done. L of f prime that we have done. And the remaining thing is integral outside. Integral of L of f. So let me state that result. So I'm assuming f is piecewise continuous including 0. Okay. So 1 by x, 1 by root x, etc. are not allowed in this case. Okay. F is piecewise continuous including 0 and of exponential order. And suppose t going from the right hand side limit of f of t by t exists. You assume this. Only then the theorem is valid. Okay. So right hand side limit as t goes to 0 of ft by t exists. Assume that, and then I have a formula for integral of the Laplace transform from s to infinity. So there is no minus sign. That is because I have put my limits properly, s to infinity. And this answer is, so you're already saying this limit exists, and then you can calculate L of ft by t that exists. That is nothing but the integral from s to infinity of the Laplace transform. Yeah.
Why did you choose limit t tends to 0 plus f of t by t exists?
That comes in the proof, I think. We will see the proof. Okay, you need that assumption. Okay, so let's see the proof. So you start with this thing, integral s to infinity of fx dx. What will be your next step? You tell me. There is an obvious next step.
Equal to L of g of x.
Hmm?
Let us assume equal to L of g of x.
No,
we can substitute
no.
capital F as the Laplace expression.
Yeah, you have the
0 to
definition of f of x, no? So you plug that in. So you'll get a double integral. So what is f of x?
integral 0 to infinity e power minus st f of t dt.
Correct. So I have just plugged it in 0 to infinity e power minus xt ft dx. No, fx dx, right? So e power minus xt ft dt multiplied by dx. T is going from 0 to infinity, x is going from s to infinity. Okay. Now I have changed the order of integration, which is okay with you. Let us assume that everything is nice. Under given conditions, you can change the order of integration. You cannot always change the order of integration. Okay, that requires, one argument, but under all the assumptions given, it is true. So we can change the order of integration. Now what will you do? So I'm integrating with respect to x first. So what is the so integrating with respect to x, you can do this first, no? You can do s to infinity e power minus xt dx. So integrate that. What is the integral of e power minus xt dx? What is that integral?
Minus e power.
Yeah, e power minus xt by minus x, right? By minus t, sorry. So this is integral 0 to infinity ft times e power minus xt by minus t from s to infinity dt that you plug in. So maybe a little bit is going down, but you can see 0 to infinity e power minus infinity, that is 0 minus of minus. So e power minus st by t ft dt. Okay. And this ft by t is a good function, limit exists, etc. And that is enough for you to show that this integral exists. And this integral is what is written as?
L of f
Written as
Function of
L of ft by t by definition. So this is also easy. You just plug in, it's a double integral, change the order of integration. So if I ask you, what is a key thing to remember in this proof? What is your answer? There's only one thing to remember in this proof, which is
Change the order of integration.
change the order of integration. Change the order of integration. You'll get a double integral, and what you need to remember is change the order of integration. Everything else is automatic. Okay, there is only one natural thing you can do, and that you will do. So change the order of integration is the key word here, key phrase here. Okay, so you have this also. Let's do an example. Find L inverse of log 1 plus w square by s square.
Sir,
Yeah.
where did that point came? I mean, t tends to 0 plus once.
See, you wanted that, you wanted this integral to make sense. Okay, and there you are using that. You wanted, ft by t to be a well-defined function. See, if ft by t was blowing off towards 0, this improper integral is not, right? If ft by t in the limit going to 0 was blowing off, going to infinity or something, how do you do an improper integral? It is a to b and limit a going to 0, right? So this would have created a problem. That is why you threw in this assumption. Okay, for the integral to converge. If ft by t, if the limit exists, then everything is nice, and therefore the integral exists. That's where you used it. Okay.
Yes.
So let's do this example. L inverse of this. What strikes you first? In log 1 plus. So w is like your a. S is your frequency variable. What strikes you here? See, always you need to get something, some idea what might involve in terms of non-functions. What strikes you here?
Differentiating the Laplace.
No, even before that, which function is the function
Cos.
in all these things that you know? Sine or cos, right?
Cos, yeah.
Do you see w square plus s square here?
Yes, sir.
Yes, sir.
Because
Yeah,
1 plus w square by s square is s square plus w square by s square. But s square plus w square in the numerator, you know nothing, no? S square plus w square in the denominator is what you know, right?
Yes, sir.
So how will you reach there?
Sir, by inverting the order and taking minus outside.
Yeah, but inverting, how do you naturally get the thing inside log inverted? How do you get it inverted inside log thing?
Differentiate.
Integrate.
So this can be written as the integral of some.
Differentiation.
One of these things you have to use. So what I'm going to use is finally this idea that I will, okay, I'm yet to reach here. So the first observation is, if I want to get s square plus w square in the denominator from this function, what do you have to do to this function?
Differentiate it.
Differentiate with respect to?
Yes.
S. Of course, s is the variable, w is a constant here. So differentiate with respect to s, you will get s square plus w square downstairs, and that will be good. So what is this answer, d by ds of this? Can somebody quickly do it on a piece of paper and tell me?
Minus 2w square by s into s square plus w square.
Very good. So this is good, no? This is in a shape that you understand, right? Now you can either do 1 by s square plus w square, find that Laplace transform and integrate that in order to get divided by s. Or you might just do what? You can do it in two ways. 1 by s square plus w square, so get that thing and integrate that in order to divide by s. That is one way. Another way is
Partial fraction.
partial fraction. So let's do partial fractions. Is this correct? This looks correct,
Yes.
no? Okay.
Yes.
So now both sides you know well. So what is the Laplace transform of inverse Laplace transform of minus 2 by s?
Constant function.
Constant function?
Minus 2.
Minus 2. What is the inverse Laplace transform of 2s by s square plus w square?
2 cos omega.
2 cos omega
Yeah,
t.
it is W, 2 cos WT. Okay. So I have written it as minus of L minus L of 2 minus 2 cos WT. Agree? Therefore, I'm not interested in Laplace transform of this one, right? I'm not interested in this. I'm interested in inside thing. What will you do?
Integral of LHS is 1 by t.
Yeah. So this answer is nothing but integral of d by ds of this, right? Integral, if you take, you will get this answer. So you are taking integral of this, and in terms of this, what should be the answer?
Divide by t.
Divide by t inside, right? Divide by t, of course, divide by t makes sense only inside. So what you have done is, I have taken L of 2 minus 2 cos WT divided by t. So this is L of ft by t, and L of ft by t, the answer is, L of ft by t, the answer is integral s to infinity L of f. Integral s to infinity L of f. And that is, oh, is there a mistake here? L of ft by t is integral f. So L of
So
ft,
there's no mistake.
no mistake, no mistake. L of ft by t, yeah.
Something
L of, correct. So L of minus of this is integral of this.
yes.
So
Here it is.
here there is a mistake, right?
That this one is right.
No,
The
there's
second
no.
one is right.
No mistake. All correct.
After equal to only, I think right.
My formula is L of ft by t is integral of the Laplace transform from s to infinity. So L
But
of,
we don't know directly. I mean, we can't write directly LHS as that one, no? After RHS one, we need to write
correct,
like.
correct. So RHS is what I'm doing. RHS is what I'm doing. You are right. So integral s to infinity of the Laplace transform. Integral s to infinity of, I'm applying that formula. I know that formula. So I'm okay. Forget this one.
That is correct only.
This is integral s to infinity L of minus of this, right?
Yes.
And this would be integral s to infinity of the Laplace transform will be L of ft by t. And yeah, this is correct. This is the Laplace transform. So this is this. Okay.
But minus sign will be no.
Huh?
What about
Minus sign should not be there, I think. Yes.
sir,
Correct. Minus should be there where?
here minus should not be for this equality should hold.
Here minus should not be there.
Yes, sir. Since we are doing divided by no, that's it. Why minus sign will be extra?
Okay. Because I put the minus sign here, it is confusing to me. What this means is L of 2 cos WT minus 2, right?
Yes, sir.
So what we know is L of 2 cos WT minus 2, if you integrate from s to infinity, that is exactly this. The answer will be L of ft by t.
2 cos WT minus 2.
So there's a sign error.
Correct.
Sign
L of,
error.
yeah, that's correct. So this is also with a minus sign. This is also with a minus sign. 2 cos WT minus 2 by t. Okay. So there's a typo here, but that gets corrected here. The answer, this is correct. This equal to this is correct. Because, no, maybe there's a typo. I will correct it if there's a typo. So
right, but first term equality is wrong.
this equality is wrong, right?
Yes, that equality is wrong.
This equality will be with a plus sign.
Yes, then here it should be minus again.
So now let us.
Sir, the minus sign should not be there in the front of the integral there.
Yeah, that's what the other person also said. I will correct the appropriate thing, but the point is, so let there be a minus here. I will correct here if necessary. So minus of this integral is what? You are integrating this. That is integral of d by ds of this. So what is the answer? Integral of d by dx of log 1 plus w square by x square is by fundamental theorem log 1 plus w square by x square, right? And that the limit is s to infinity. That the limit is s to infinity. So what will you get? You will get this one evaluated at infinity is 0 minus This one evaluated at S. So you will get minus of this, right?
Okay.
You will get minus of this, no?
Yes, sir.
Correct? Yeah. So that's correct. So what is happening is there is no minus sign here and then this is correct, no?
Yes, sir.
Yeah. So there is no minus sign here and then this is correct. Here there is a minus sign. Okay. So here there is no minus sign. So I have multiplied by a minus. So multiply by a minus, this goes away. And this one comes with a minus sign and that minus goes away. So everything is fine. So I need to correct one typo here, which is just delete this minus. All right. So this is, you are using this method now. So again, the most important thing is once a function is given, you have to really stare at it and see which one is in terms of functions that you know. So here the idea was, look, there is log of something in which I see an s square plus w square, but I would like s square plus w square down in the denominator. Only then I can play around, and that is what motivated you to do all these things. Okay, I will correct this typo. And so you have got the answer. So the answer is correct, no? The inverse Laplace transform of this is 2 minus 2 cos wt by t, not minus of this. The typo is here. Okay. So very good. So up to now we have seen L of f prime, L of integral of f, LF prime, integral of L of f, because it's very, very important. I hope I'm not boring you. Let us recall once again. F prime is derivative with respect to t inside, that involve multiplication by s outside. S is always outside, t is always inside. L of integral of f is integral of f with respect to t inside, that involve division by s outside. L of f prime is derivative outside, and that will involve multiplication by t inside. And integral of f, LF integral is outside, that will involve division by t inside. Okay, so very symmetric, very, very beautiful. And all these were useful in finding L inverse of a given function. I have not done so many problems. You should do many, many problems. So what I say is maybe the tutorial booklet has a lot of problems, but that's not enough. That's not enough. So what you should do is, some of you can cook up problems and, ask others. You cook up your own problem and then solve your own problem. Okay. Be very, very comfortable. And I also, in the interactive session, I told students how to get even more problems. So let me quickly share the screen and show that also. Of course, many of you will know this. So how do I share? So let me open it first and then I will share. So I showed this in the interactive session last time. So many of you know about this website, right? It's a very beautiful website called Stack Exchange, math.stack exchange. You know this? How many of you know about this? How many of you have heard about this website?
Sir, are you sharing?
I will share now. I just opened it and now I will share. So can you see? Can you see the website?
Yes, sir.
Firefox page. And have you seen this website? Many of you know about this?
Yes, sir.
So maybe I will increase the font size. So here, all kinds of undergraduate mathematics is there. Maybe, slightly more advanced also, but everything is here. I mean, lot of questions are there, but how will you get to our course? So you can either use their search, but what I find is, Google search is better than their search. So you know how to search inside a website using Google? Yeah. How many of you know to search inside a website, any website, New York Times?
Yes,
So how do you do that? You can do site colon this thing and you can type your keyword. So suppose I type Laplace transform. So I made a spelling mistake. Yeah. Okay. So you will get, every hit you can see, right? All the hits are from math.stackexchange.com. And you will get a lot of problems. And, you can also clear, your theoretical doubts. So now, if you have one more problem, you can, type that and see. So you have to, you have to do it. Okay. So you will get a lot of problems here. But another important way in which you will get a lot of problems is you cook up your own problems. Okay, that's the best way. You take, you make your own problems, ask natural questions and apply all this theory. So do a lot of problems. Okay, I'm not talking just about this course or our NSEM. Beyond that, it's an important topic. And since anyway you are, taking the effort to learn this in this course, why not understand it thoroughly? So do a lot of problems. Okay, let's continue. I wanted to tell one more thing, but I'm blanking out. I wanted to show you the stack exchange. Yeah, if I remember it, I will tell you. Okay, I suddenly forgot. Cannot be all that important, in which case I would not have forgotten. So all these were useful in finding L inverse of a given function. The idea was to, what was the main idea? Is there a real method or is it more your experience in applying all these formulas? What do you say?
Experience.
Experience. You need a lot of experience. So the idea, as a slogan I am highlighting, the idea was to, so for example, in the very last example, what strikes you is, look, there is a w square plus s square and you can make it in the denominator by differentiating, etc. So the idea was to, first you have to spot the obvious. So spot the obvious in the question, and then what do? You modify. So get hold of something and then you tinker with it. Okay, then you play around with it. So spot the obvious and modify is the only method. As I told you last time, I showed you that on Wikipedia that there is a specific formula for the inverse Laplace transform. But I also, read it aloud. No, in Wikipedia itself, it was written that that formula is not useful. In order to, that's a theoretical formula, but practically it's not useful. So practically the idea is to do this. This is what is going to help you. This is why I said, like in childhood, you have learned multiplication tables by heart, right? 7 into 6, if I ask, you don't think, no? Without thinking, you say 42. That level of comfort you need with Laplace transforms and inverse Laplace transforms and using all these formulas. Okay, there may be many ways of doing one particular question. You might do partial fraction, you might do integration, you might do differentiation, up to you. Any one method is enough. Okay, so spot the obvious and modify. This is where you have to be very, very comfortable using all these relations. I cannot teach you this. There's no way in which I can teach you this. I can only, give some examples and illustrate how one is doing this. This is practice. This is completely practice. In doing all these things, it will be of great help if you can do the following. You have a function of s, L of f. You have another function of s, L of g. Suppose you take, so what is this dot? This is just the product of two functions. You can take product of two functions, right? Suppose you take the product and you would like to know the inverse Laplace transform in terms of f and g. If there is an answer, do you agree that it will be extremely useful? Right? Because inside now, if you see 1 by s square times something, and that's something 1 by s square also then it is the product. So in terms of those functions, if you can write down the inverse Laplace transform, it is going to be very useful, right? Do you agree?
Yes, sir.
Okay. There is an answer to this. Can you tell me the key word in the answer? I said it already at the very beginning, verbally.
Convolution.
Convolution. I don't know the pronunciation. Convolution. Convolve. Okay. So have you seen this notion somewhere else?
Yes, sir.
Maybe some of you have done a little bit of Laplace transforms in some other course. You could have seen this. So what is the meaning of convolve? What is the English meaning of convolve? Where have you heard this word convolve in plain English speaking? What is convolve?
Combine, right?
Convolve is not combine, no? Okay, so when one asks for a specific, though I know what it is, I don't know enough to explain. So let us check the dictionary. Okay. So
Anything that is complex and difficult to follow.
yeah, this is my impression. You said it. So the only thing that occurs to me when I say convolve is, oh, that is a convoluted argument. What does that mean? They can be a simple argument and you are giving a very, very involved argument. That is called convoluted. Twisted. So let us see the proper meaning. Convolve. And
dictionary already.
let me share the screen. Convolve is, can you see the screen?
Yes, sir.
So it says roll or coil together, entwine, and or in mathematics combine with another by forming their convolution. But what is good is not this mathematics meaning of combine. What is good is this one only. Coil together is what is really giving you that flavor. And how do you pronounce this?
Convolve. Convolve.
Convolve. So what I said is almost correct. Okay. So here is convolution. So this is the formula. If this is the notation f star g of t, the definition is, anyway, it's coming in my slides. Let me show my slides only, my notation. So I need to share again, I guess. Yeah. So this is going to be very, very useful, very important concept. Some of you will study Fourier transform later, and then also the same notion is very useful. Okay. So fortunately, there's a very, very nice answer to this. And this is going to be denoted by, this is why I came to my slides. I did not like, the way they put star on that page. Did you also not like it? On the Firefox page, the star was not put properly, no? The star was coming somewhere above. I wanted it symmetrically to come in the center. So that's why I came here. Okay. So this is going to be f star g. This is a notation where star is what is called the convolution operation, convolve. Okay. So let's define it. So the convolution of two functions ft and gt is defined as f star g of t is, there you saw minus infinity to infinity or something, but this is my definition. Okay. 0 to t. F of t minus x gx dx. So you might, yeah, this is correct, no? So you are integrating with respect to x. So x goes away. What remains will remain. What remains will remain. And you could have, a better way of writing this would have been, you could have put this to be y. No, sorry. Is this correct, the definition?
Yes, sir. It seems correct.
Well, even if I did see a minus infinity to infinity there, no, on the wiki page. Let's just double check. It should be correct.
I think
Sir, actually, they consider it to be 0 for negative x. So probably they.
No, but still, there's a big difference between what they have written and what I have written. Let me check the. Can you see the screen again?
No, sir.
No. Okay. So I think I'm not very comfortable with sharing, but I am on the wiki page, and yeah. Okay. So it is explained here. So let me share. Okay. Yeah. See, you know how even your teacher is getting confused suddenly. See, one thing that I'm not doing is I'm not looking at my slides before coming to the class. Okay. I'm also experimenting in terms of teaching. You know what I thought was, can you see the screen now?
Yes, sir.
Yes, sir.
What I thought was, anyway, I have the slides. As I told you, I have taught the course in 2016. So I do open the slides typically the previous night, or if the class is at 11:30, I open it this morning because there's enough time in the morning. And I do change the date and all that because I don't want 2016 in my slides. I do such things. And I also quickly go through the slides so that, if the spacing is not correct, 2016, my aesthetics could have been different. No, paragraph break and some English words I change and all that. But mathematics, I'm not really reading. So actually I should, right? Because I'm teaching and I should be on top of the material. And I used to do that. So when we started the course, I was doing that. When I was teaching you undetermined coefficients and all, I was doing that. But when it came to Laplace transforms, I thought, let me not do that deliberately for two reasons. One is that I really like Laplace transforms and I wanted to know how much I remember without looking at it. Okay. And second reason is, this is so much experience. This is not so much theory, most parts of it. So I thought, let me be with you so that if I read it ahead, then I'm ahead of you. No. So I thought, let me not do that. Let me make mistakes in front of you and let me correct it. After all, the final slides will have no mistakes. So that's why I'm getting confused. I'm not looking at it just before the class. So I wrote this, right? Is my highlighting working? No. So maybe I have to highlight from here. This is what I wrote, no? In my slides, this is what you saw, right?
Yes, sir.
Okay, so this is indeed correct. So I don't need to change the slides, but you are also seeing this, see, as an integral transform like this, minus infinity to infinity. And equivalent definition, again, minus infinity to infinity. So what is the argument given?
So normally, they often define Laplace transforms for functions from minus infinity to infinity also.
That
So in
is
those cases,
possible, yes. Yes,
these
that is
kind of
possible.
expressions will arise.
Yeah. So once you are defining on 0 to infinity, then the integration limits can be truncated, resulting in this. So these are equivalent definitions. So it's okay. So maybe there's a small check to be done, which you can do or I can do later. Okay. So I just wanted to make sure that there's no crucial mistake in the slide, which we have verified. Let's go back to this. Anyway, I was confident they shouldn't be a big mistake, because such a big mistake would have got corrected in 2016. No, some students would have told me, or I myself would have corrected it. I was confident, but I wanted to be doubly confident. Okay, so this is the convolution for us, 0 to t, f of t minus. This is why, this is the entwining that I'm doing, entwining or entangling or whatever. See, you're doing something funny, right? You're doing convoluted argument here. You're taking x, then you are, twisting it with a minus sign. From the positive side, I mean, from one side, you have gone to the other side. X is, x is from 0 to t, and you have taken minus x and then added t, and you have convoluted it. Okay, that's what you're doing it here. And then you are multiplying again, and you have integrated, you have a formula. Okay, and there are some nice properties. The first property is whether you convolve f with g or whether you convolve g with f, you get the same answer. Is it obvious?
Sir,
Yeah.
I want to ask one thing. How you will get this one as answer if L of f of g means?
That we are yet to reach. That is the next slide, or next to next slide maybe. Okay, that is called the convolution theorem, which we have to prove. But I need to give you the definition, no, before proving the theorem, right? And let us observe some simple things. Is this obvious? They commute. Convolution is an commutative operation. They commute.
Yes,
Why
sir.
is it obvious? Because if you take g star f, what will be your answer? You will get f of x, g of t minus x dx. And you make a change of variable. What is the change of variable?
T minus x is...
T minus x is x. So that will be a change of variable. And if you put y equal to t minus x, you can check, you will get this. Is this obvious? F star g1 plus g2 is f star g1 plus f star g2?
Yes, sir.
It's
Yes, sir.
obvious, because here you will get g1 plus g2, and integral is a linear transformation. Is this obvious? F star g star h is f star g star h? Sorry, what happened? Okay, something else came. Can you still see my slides? Can you still see my slides?
Yes, sir.
Yeah. So how do you verify this? You apply the definition. So f star g is there. You do star h. You will get one more thing, and observe that that is same as this. That also is easy enough. Okay. And check this. You just have to apply the definition. There's nothing to prove. And what about f star 0? Is it clear that it is 0? Because g will be identically 0. So the integrand is 0, and therefore the integral is 0. That's also obvious. Okay, these are all obvious properties. What is the word for number 3? Do you know the mathematical
Association.
This is called commutative, and this is called
Association.
Associative. Okay, you don't need to know, but anyway. So remark is that f star 1 need not be f. Okay, you have to apply, and you have to see what it is. And here is a simple example that you can check. Sin t, if you take and if you convolve with the constant function 1, the answer is 1 minus cos t. It is not sin t. So f star 1 need not be f. And this is the theorem that we are after. Suppose LF and LG exist. I'll take 5 minutes extra so that I can finish off the topic. LF and LG exist for all s bigger than a. Suppose this is true, then L of f times L of g, its inverse Laplace transform is nothing but f star g. Beautiful. Okay, we have introduced this operation called convolution, which fits so well with Laplace transform of products. So Laplace transform of convolution of two functions is the product of Laplace transforms. So Laplace of convolution is product of Laplace. So in other words, Laplace transform takes convolution to ordinary product, usual product. And this is true whenever S is bigger than A. Okay, so let's see the proof. Proof is easy. See, in many times, in order to guess what should be the correct thing, that is the difficult part. So somebody had to think about this and somebody had to think about the operation of convolution. Once you get that, then the proof is easy. So LF times LG, let us write. What will be your next step? You tell me. If you
Write
start
it as the
with
integral.
this, what is the obvious next step?
Write it as the integral.
So LF you write as an integral, LG you write as an integral. This is what you said, right? So whenever you write, you change the variable, no? It's the same thing, but this is how you did e power minus x square integral dx, right? You called it I. Then again, when you wrote I, you wrote minus y square dy, so that, you can do those operations. So you do exactly the same thing. This is a double integral, right? This is a double integral with what I have done is, so it's a double integral gy dy, and I have written e power minus s of x plus y fx dx. What will be your next step?
How did you mix those two?
Hmm?
How did you mix those two?
I did not mix. It is the same thing.
I mean, you took the e power minus s1 into the one more.
This is the meaning of double integral. No, this is how you do integral in calculus, right? This means integral 0 to infinity, one more integral 0 to infinity, e power minus x fx times e power minus sy gy times dx times dy. That is the meaning of this integral, no? Double integral.
Okay, sir.
Because x and y are independent, right? So this means e power minus sx fx e power minus sy gy dx dy double integral 0 to infinity 0 to infinity. That is e power minus sx times e power minus sy fx gy and e power minus sx times e power minus sy. I put it together. So this is all fine. What is your next step?
Substituting x plus y equal to t.
Yes, substitute x plus y equal to t. So you will get dx equal to dt, and LF times LG will be integral gy dy. Something changed here, no? So now, earlier you had x going from 0 to infinity, and that became t going from y to infinity, because t is x plus y. T going from y to infinity, e power minus s, x plus y is t, and f of x is t minus y dt. Okay, so this is just substitution. And this, how do you do typically a double integral like this? You have done double integrals in calculus, and what you do is, so what did I do here? I took what have I done here? So you make that area and you have changed the, right? So here you have the t axis and you have the y axis.
Type 1, type 2.
T is going from y to infinity and y is going from 0 to infinity, right? T is going from, so you have something going from 0 to infinity and the other is going from y to infinity. So you draw x equal to y, right? So this is that shaded region. I'm sure you would have done many such examples. And then what you do is you change the order of integration. So something going from y to infinity and then y going from 0 to infinity will be like above that triangular region, right? Along x equal to y, it will be above that. So there you do x going from 0 to infinity and y going from 0 to t. So this is the order in which you have changed. I mean, the order has changed. So that you do, and that is e power minus st times what you see. The remaining thing is exactly f star g. But what is this? This is L of f star g. So it's an easy proof. So what is the key idea? Key idea is write down, make a substitution, and change the order of integration. So if you have to give me one phrase, what is the phrase? What is the key step in the proof?
Substitute and change the order of.
Yeah, not even substitute. I mean, okay, substitute you have to do, but the main idea is change the order of integration. Yeah, you are right. Substitute and change the order of integration. Okay, so the limits you have to be careful. In calculus, you have done many things. So when you change the order, the limits get changed and everything is good and you got L of f star g. Let's do one example and stop there. Find L inverse of this. This we have done earlier, no? This is exactly the question on my first slide, right? So when I asked you this question in lecture 15 in the last lecture, most of you said you use partial fractions. Then what did I say? I said, well, of course you can use that. Maybe that's even easier, but I would like to I would like to do this method of integration, and we did like that. Now what are we saying? We have to do convolution. Okay, so let us do convolution. L of t is 1 by s square. This you know, right? 1 by s square tells you it is L of t, because L of t power p is L of t power n is n factorial by s power n plus 1. So this is 1 factorial by s square, and L of sin at is a by s square plus a square. Therefore, L of t star sin at is what you are looking for. Correct? So the answer is t star sin at. And what is t star sin at? It is integral 0 to t minus x sin ax dx, which you can do and you will get this answer. That's an integration you can carry out. Okay, so how did we do this earlier? We did this earlier by doing a by s square plus a square first and integrating once and integrating once more. And before that, you would have done it using partial fractions. So this is just to illustrate convolution. Let us do, oh, okay. So I see that, I had something more, but we are overstepping. So I will finish with this thing. So finish with this example and continue in the next lecture. So this one, what will you do? You apply Laplace transform, and you assume that you have a solution with all those conditions, piecewise continuous with exponential order, etc. You would have got something, and you substitute, you got something. So here is something interesting. I have not told you what is G. Okay, I have not told you what is G. So what you have is L of G, which is G of S, capital G. Whatever it is, you have got this, and that you have written as partial fractions. But here you know that GS is coming still, but that doesn't matter. So you have got the answer to be 3L of cos 2t minus half L of sin 2t plus half L of sin 2t times L of G. So what is your answer Y? Your answer Y is 3 cos 2t minus half sin 2t plus half, answer is 2t star G. So whatever G is, you have solved in terms of convolution. Okay, so convolution is very useful, right? None of your other methods would have worked, no? Particular solution without telling what GT is, you cannot do undetermined, or you cannot do, well, variation of parameters, you could have integrated G. Yeah, but undetermined you can't do.
So we can use the factorization of the differential equation, differential operator. And
you can try like that also. Yes, you can try like that also, but integral G, you will leave it as integral G, which you are forced to do, which we are doing here also. So that's okay. Okay, so I will just exhibit my next slides and stop it. If you have questions, we will come back and discuss that. There is no time to go through it carefully, but let me just put the slides across so that it will be their own model and you can look at it. I'm not doing anything for this course. I'm just recalling your +2 partial fractions, because in this method, we will have to do partial fractions a lot. So I have done, a complicated looking partial fractions explicitly in order for you to recall what you did. So you will write it as a polynomial plus a polynomial by polynomial. Because 9 is bigger than 7, you will do your usual division. You will get a remainder, which you will write as P2x. So you got that explicitly. And then the denominator you will factorize and you will solve for this only. This part only you need to do. This part you don't have to do. And how will you write this? Can someone tell me? Partial fraction, how will you try to solve this?
A by x minus 1 plus b by x minus 1 whole square plus c by x minus 1 whole cube plus dx plus c by x square plus 1 plus fx plus g by x square plus 1 whole square.
Very good. So you write like that: a by x minus 1 plus b by x minus 1 square plus c by x minus 1 cube plus dx plus e by x square plus 1 plus fx plus g by x square plus 1 square, and solve for a, b, c, d, e, f, g, right? That's how you do it. And that's what you should do. And one more observation that you can do is, suppose fx takes such a nice form, okay, coefficient by x minus xi square, etc. Then you can get this coefficient easily using derivative differentiation. This you can observe. This is true. from your Taylor series or by directly taking derivative, you can observe this. And in particular, if xi is a simple root, this takes a very, very easy form. What is the meaning of a simple root? What is the meaning of a simple root?
Something real like that.
No, simple just means multiplicity 1. For example, x minus 1 has 1 as a simple root. X minus 1 square, 1 is not a simple root. 1 is coming twice. Okay. So if xi is a simple root, what will happen is this will be of this form where when fx is px by qx. What all I want to do is, here is one more method using derivative. If you want, I will discuss this in the next class, but you can read it in the slides. So what I'm saying is, here you have such an fx, and this fx, you can, if you can write like this, then the coefficients can be obtained using derivatives like this straight away. So you have two methods. One method is what you told me here, in which case you will have to cross multiply and solve for this. There's another method where you can easily get the coefficients by using derivative of these things. Okay, you need to do a small check. So here is an example. If you have such a thing, what will be your first method? Your first method will be, how will you write it? In your first method, what will you do? You will write it as?
Partial.
Yeah, partial fraction. How will you write it? A by?
X plus 1 plus b by x minus 1 plus cx plus d by x square plus 1.
Correct. Whereas in this case, I have written it using complex numbers, but I can combine it later. So this x square plus 1 I have written like this. And now this can be decomposed into rational functions whose denominators are x plus 1, x minus 1, x plus I, x minus I. And you can club x plus I and x minus I together again, because your final answers should be only in terms of real functions. So because each term has power 1, this is what I meant by simple root. X plus 1, it's a simple root. It's not repeating. In this case, xi is minus 1 plus 1 minus I plus I. These are the roots. So what you are doing is, you have written pxi by q prime xi. So xi square minus 5 by qx is this polynomial. So this polynomial you take and you take the derivative. So you see that, so x power 4 will give you 4x cubed, right? And you can plug it in. So these are the roots, minus 1, 1 minus I. You take the derivative and you plug it in. And I know that I'm not doing this correctly because time is up. I'm doing it fast. Just try this method. This method also you can get it and you would have got some answer. And will you write this? Will you leave it like this? Will this be your final answer?
No, sir.
No. These two you leave it like that, and these two you combine. These two you combine and you will get something. Okay. This has nothing to do with our course. Just recalling some partial fraction techniques from your +2. Okay, there are two methods. Both methods you can be comfortable. I don't know which method will be easier in which context. Okay, let's stop here. I have exceeded time. Sorry about that. Let me stop sharing the screen. No, how do I stop? Yeah, stop sharing the screen and also stop recording. Stop recording.